Everyone. Hi. Thanks. Let's get started. So today, oh, yes, I am recording. Okay, we are done with single-threaded programming. We're done with talking about caching models, and we are moving on to multi-threaded programming in shared memory. And I think the cluster is back up, so you should all be able to start your homework now. Okay, so you can remember this picture from the first lecture. This is a high-level abstraction, like a cartoon of what a shared memory multi-thread looks like. You have one memory, and you have a network that connects all the processors, and you have all these separate processors connected through the memory. And all of the processors use the same memory so they can have shared values. And this is like a picture of an actual chip that implements the shared memory multi-core architecture. You have the shared L3 cache, and you have a bunch of different cores, and the cores can all act independently. And the shared memory multiprocessor connects the processors in one memory system, and all of the threads can access the global memory space. And so, like I was talking about in the first lecture, why do we have this trend towards multiprocessors? Because of Moore's law and the scaling of clock frequency. I showed something similar to this before, but we can just remember why we're doing multi-threaded programming. We had this trend of transistor count increasing by about 2x per year, and a similar trend that followed of the clock speed increasing about 2x per year, or 2x per every 2 years from what is called Moore's law. But now in recent, I guess not so recent anymore, transistor count is still going up, but the clock speed is not increasing anymore proportionally. And the reason that it isn't is because of power scaling reasons. So this is like a popular picture that everyone shows in these classes, but had power density increased at the same rate that it was before, it would have been going at an unsustainable rate for cooling. And so we couldn't continue increasing the frequency, and performance can increase as a function of both cores and frequency. So frequency is just the clock rate, like how many cycles can you do per second, and cores is the number of processors that you have. And the performance increases both proportionally to cores and frequency, but the power increases more proportionally with the frequency than the cores because of physical reasons. So that is why we are increasing the cores now. And this is the increase in power as a function of time and the increase in cores. So you can see this is like about 2005 or so, but there's a starting, like vendors started increasing the number of cores on their chip because of power limitations. So that was all review, and this is like the similar multi-core architecture, the same cartoon, but just in a slightly different way. So we have memory and I/O, and then all of them are connected by a network, and we have several processors that are shown by P, and each processor has a local cache attached to it, as well as a shared memory. So this part is accessed by all the processors, and this part is private to each processor. Okay, so when you implement these multiprocessors, one main issue is called cache coherence, which is how do you manage the cache in the presence of multiple processors, and how do you keep a valid copy of values in each of the processors such that nobody has an old version of a value. So in this example, let's say the leftmost processor was loading X. So in this case, X is 3. Now the second one wants to also load X, and they loaded them from memory. So up there is the memory. And again, like this one loads X, and X is 3, and they all have it in their local caches. But now suppose that this rightmost processor wants to do some computation, and then they want to update X. So now they say X equals 5, and they want to store it back into the memory. So first they would store it into their cache, because the cache is like the closest thing to them. But now suppose that the leftmost processor wanted to load X again, and update a copy of it, and the X equals 5 has not been written back to memory yet. So their copy of X equals 3 is invalid, and you need a way to tell which copies you have are valid and which ones are not at any given moment in time. And the most basic way to do that, so the most basic cache coherence protocol is called MSI. And in MSI, each cache line has a state. So M stands for the cache block has been modified, which means that no other caches can contain this block in M or S states. S stands for sharing, so it means that other caches can share this block, and I means invalid, and it's the same as not there. So if you have a line that is invalid in your cache, you can't use that value because it has been overwritten somewhere else. And basically the way that MSI works is before your cache, if you have a processor cache and you want to modify some value, the hardware first has to invalidate all the other copies in everyone else's cache because their copies are no longer valid. Okay, so this is an example. We're going to focus on Y. So here everybody has Y in S state, which means shared. And suppose that the second one wanted to store Y equals 5. And before you can store Y equals 5, then you have to update everyone else to be invalid. So now this one became I, and that one became I. And then only after you invalidate everyone else, then you can modify your own Y to become 5 in the local cache. So that was cache coherence, and that is not something that the programmer has to manage, like that's implemented underneath. Like if you write C or C++, you don't have to manage that, but that's just what's going on underneath when different processors modify the values. So yeah, so now I'm going to talk about how we do programming in for multiple threads. So these days we don't program directly on processor cores, which means that like we have these abstractions of threads and we don't have to directly manage them because it is really annoying to manage them directly. And basically there are several concurrency platforms which abstract these processor cores, and they under the hood handle things like synchronization and communication between the cores. And they also often can perform load balancing under the hood for us. So some examples of that include pthreads, Silk, which is a C-like language, and OpenMP. And the main one that I'm going to be talking about today is OpenMP, but I'll talk a little bit about pthreads also. So I want to use this example of computing the Fibonacci numbers to illustrate how we do multi-threaded programming. So the Fibonacci numbers are the sequence. Here are a couple of examples like 0, 1, 1, 2, 3, 5, 8, and so on. And you compute them by this recurrent relation. So the first Fibonacci number is 0, the second one is 1, and later on you get them by summing the previous two. So that's how like the third one is 1, because 0 plus 1 is 1. So yeah, so that's how you compute that, and you can express it with this recurrence relation. And you can directly implement this recurrence relation. Just in this is serial C, like this is just straightforward C. You have this fib function, and it takes in a parameter n. And if you're in the base case and it's less than 2, you return it. Otherwise, you call fib n minus 1 and n minus 2, and then you sum them up to get your answer. And yes, this is not the most efficient way to compute fib. This is like an exponential way to compute it, and clearly you can compute it linearly, but it's a good example for how to use the parallel constructs. So we're going to use this recursive function for now. And this is just like the test driver. You take in n, and then you call fib n. So, yeah. That's how the serial code works. Okay, and that is the recurrence tree. So if you have fib of 4, then you would branch into fib of 3 and 2, and so on. Fib 3 becomes 2 and 1, and then in the base you have 1 and 0. And then you just return n as your base case for it. And the main idea for parallelization, and overall, I use just in this function, but overall in general, when you want to parallelize things, the key idea is you want to find independent things that you can do. So here, fib of 3 and fib of 2 are independent. Like they don't relate to each other in any way. They don't share data. You can, those are just like arithmetic calculations. So you can do them in parallel, and you can do the branches of all the branches of this recursion tree in parallel. So pthreads is one of the older ways to do multi-threaded programming. It's the standard threading API. Everybody pretty much has it if you have like an x86 processor. And it is a bit more like do it yourself than other concurrency platforms, in the sense that you'll see in the code, like it's more manual than the other ones. You have to manually create the threads and tell them what to do. Whereas like things like OpenMP are more, they have easier programming, they're easier to program. And each thread implements an abstraction of a processor, and under the hood, the machine tells you, under the hood, the machine maps the threads to different processors. And you can communicate with your threads through shared memories. And you don't have to manually do inter-threaded communication. So the main things in pthreads, so it's like, you can even see that this looks a little bit old-fashioned, but there's two things, there's create and then there's join. And when you want to use a thread, you first have to create it. And so the parameters of the create are, you have the thread that you wanted to create, you have some attributes, normally it's just null, and you have the function. So the main important parts in create are the thread and the function. This is like a void pointer to a function. And this is the function that you want to run with your thread, and arg, which is the arguments to your function. And then join is how you like exit the threads. That's how you tell that they're done. So when you call join, you add the thread that you want to end, and then you have some status, which you usually ignore. But status just tells you like if something's gone wrong. Yeah, and this is basically like how the execution flow looks. So you have a thread, you name the thread, and then you create a thread, and now you have several worker threads that you created with that create. And now they keep doing stuff, and then you join them back once you're finished. Okay, so this is the original serial code that we just looked at. And this is like the main fit function that we just had. And to do it in pthreads, here is the thread args that I was talking about. So you need both an input and an output for your thread args, because you have to capture what n is going in and what your fib number is coming out. Yeah, so that is the thread args and thread func, which is what function you're going to call when you call your thread. And your input I is taken from the thread arg. So that's the input, that's just the fib number that you want to, like the fib index that you want to compute. And the output is going to be the result of fib of I. And then you just return null because nothing wrong has happened. Okay. So looking at the right side, which is how you actually use the pthreads, the way to read this is, so if n is less than 30, then you'll just call the serial version, because there's no point in doing multi-threading if there's not enough work to do, because there's overhead to creating the thread. So first you have to get the input into the args. So you just set it, args.input over here, which is what you're going to pass into next when you call thread create. Okay. And then now you create the thread to execute fib n minus 1, which is this. So you set the input already to n minus 1, and the thread has been declared up there, and you just pass in the same function that you called over there, and the args have just been set. And then you spawn the thread, and you still have the main thread that continues on. So after you've created this thread and it forks off and starts doing its own thing, now the main thread can just continue and do the other part of fib, which is fib of n minus 1. Okay. And then you call pthread join to wait until this thread that you created finishes up. So you call pthread join, and this is the thread that you created up there, and then you call it here to wait until it's finished. So you can't continue past this line until this one has finished and exited. And then here with status not equal to null, you just check if something has gone wrong. If not, then you add the result. So previously you computed fib of n minus 2, and then you just add fib of n minus 1 into that to get the answer. Okay. So that is how you do it with pthreads. So there's several issues with it, but that's like the most original way. Like you are probably going to get pthreads on every platform you have. So if you don't have anything else, you always can do this. The overhead is an issue. So there's cost of creating threads, and usually that takes over 1,000 cycles or 10,000 cycles. So you have to, like I showed, you have to do some coarsening to make the base case pretty big and do it in serial. And the second issue is scalability. So your fib code in this example is only going to get 1.5 speed up on 2 cores, and ideally you would get 2. So you have to make it more efficient for more cores. Another big issue I see is modularity. So you see like you had to write the separate thread func, which uses fib, but now the entire function is not encapsulated in fib, like you had to call something separate. And it was also somewhat annoying that we had to set the thread args manually ourselves, even though it was already in the fib function, but we had to like populate the struct and pass it in. So it is usable, like it will work, but in terms of programmability, it's a bit, you could improve upon that. So yeah, so one of the more I think these days the most popular multi-threaded programming framework is OpenMP. It was first introduced in '97. It's a specification by an industry consortium, and it's available in several compilers nowadays. So it's pretty popular. It just comes with your GCC. ICC is a proprietary compiler. Clang and Visual Studio. I think Clang is open source. The Visual Studio is not sure actually, maybe not open source. Anyway, it is a pretty in terms of programmability, it's a pretty straightforward extension to C, C++, and there's also a Fortran version in terms of compiler pragmas, which are lines that you insert into your code, like next to the functions, and I'll show you what that looks like. It runs on top of the native threads in your program, so you don't have to manually create the threads anymore like we did in pthreads, and you can do loop parallelism, task parallelism, and pipeline parallelism. So there are 3 main things that you can insert into your code or use separately to use OpenMP. So the first one is called compiler directives, and those are things that you insert into your code. And those are like specifying the variable scope, so whether your variables are private or shared across the threads, and parallel tasks and parallel for, which you just insert right next to your parallel for. And there are runtime libraries and APIs, which are like OpenMP set and get threads, get thread number. So you can query what thread number am I, you can get how many threads are currently running. And yeah, and there's environment variables, which are not set in the code, but those are set in the terminal level. So you can set the number of threads that you want to run. And you can also set the schedule, which is how you allocate the work across the tasks. And the way that the actual threading works is similar to pthreads. So again, you start with a single process and you keep going sequentially until you get the first region construct, which is in your code, you'll tell the compiler where is the part that can be parallelized. And you have fork, which means that the main thread then can create parallel threads to do the code in the parallel region. And then you have, once you're finished, it has join, which then completes the statements, and then they synchronize and they terminate, and then you continue executing sequentially. And you can have a bunch of parallel regions, and they don't all need to have the same number of threads. Like here, it's 3, and then 4, and then 2. So it doesn't need to be a fixed number of threads, and it can also be, you can have an arbitrary number of parallel regions and also an arbitrary number of threads. And you don't have to manually do this fork and join, like we were manually doing it in pthreads, but here it's just done under the hood for you. Okay, so the way that you use it is you include this header openmp.h at the top of your file, and you use this compiler pragma openmp something that I'll show you some examples, and then you compile it with fopenmp, which is like the compiler flag, similar to where you would pass in like O3 or O1, stuff like that. So it's, in terms of ease of use, it is pretty easy. You just have to add the include, and then you add the flag, and then you're pretty much good. So going back to this fib example, this was our function. We had the base case, and we have x and y, and we want to compute x as fib of n-1 and y as fib of n-2. And the way that you express this in OpenMP is with these pragma compiler directives. And here this is pragma OMP task shared. And task is like, you're saying that this is a separate function that you can spawn off like we did with the pthreads. And shared means that the variables x and n, x is here, and n is the input, are shared across all the threads. And again, just OMP task shared, but with y instead of x. And then this, oh, I guess I have pointers to this actually. Yeah, task is all independent tasks. Shared is declaring the scope of the variable, and you don't always have to declare the scope. Mostly variables are shared except for like mostly iteration variables. And the last one is task wait. So task wait means that you have to stop at that point where you said task wait and wait for anything that you spawned off above with task to complete before you continue past that line. Does that make sense?
So are those shared, they not connected now, right? So we just say that it's shared for X and then for separate thread, it's shared for Y and then, but it's not shared in between.
Yeah, it's not shared in between. It's just shared. Yeah, like here, like these two tasks are separate.
And just to clarify, there's 3 threads in this example. This is the main and the 3 spawn, or would there be 2?
Here there would be 2 because, well, actually underneath, like if you think about, there are more than 2 eventually, because when you think about what happens here, you go back up here, and then this one is going to spawn another 2. So there can be, you have like a thread pool underneath, and you have however many tasks you've spawned, and then something underneath assigns the tasks to the threads.
That makes
Good question. Sorry, I think there's another question. Okay.
So those like pragmas, that's not C code. So like what's happening? Like how is like what am I asking? It's like that OMP like header, is that like generating new code like when it sees the pragma, or like what is happening there?
Is it generating new code when it sees the pragma? It is assigning the code block to like the threads underneath.
Okay, okay.
It's not,
Is that like the compiler doing that, or is that like when it, or yeah, I guess that's the question.
is it the compiler doing it?
Yeah, I suppose when compile parses your code, it sees like the pragma identifier, and then it's actually like executing this OMP thing. So basically, yeah, I think it's on the parse level of the compiler.
Yeah, so the compiler like once you insert these pragmas, the compiler like splits up the tasks, but the compiler doesn't do the load balancing or stuff like that.
Sure.
There's an underlying runtime system that manages that. Like that underlies, sorry, the runtime system manages the mapping of the tasks to the threads, and then the compiler divides up the tasks.
When we are trying to create a task, but thread, follow the thread.
It will, you have like a task queue, and somehow eventually when a thread frees up, it will take like the next thing from the task queue.
Just curious, how is the performance of this compared to a bottom up approach of the data?
Sorry?
How is the performance, like time taken, compared to a bottom up dynamic program?
Oh, for fib?
Yeah.
Poor, but this is just like an example of how you would do the constructs. This is not how you would actually be interested in implementing fib. This is like doubly exponentially off. Yeah.
So it won't cause a fork bump, right? Because we have a certain number of threads, but we have far more tasks, and we just align those tasks to the thread.
Yes, you can have more tasks than threads. Why is X shared? Because if it was private, there's some like, well, I'll later explain what private means, but private usually means like it's encapsulated within that task. Like the changes that you make within the task don't persist after you execute that thread context.
Yeah, but the returning exercise, so X and Y can be thread local and private variable.
Yes, but like once you get out of the task wait, you want to keep the value of X that you computed for fib n-1.
Is there any flexibility in this, or just running difference? For example, task wait, would you have to wait, but in that case, you're waiting for all the tasks to declare above to finish.
Mhm.
Is there any other ways you can declare the tasks to finish and just all of them? Like what are the cases in there?
Actually, yeah, I think p-threads you can, Yeah, as you say, like in pthreads, you can ask arbitrary tasks to finish, but here you have to just wait for all of them. Yeah. So you do lose some, but that's why pthreads are not in the fork join model, because you can have like weird truncation of your tasks. They don't have to follow it like a DAG.
What if we keep on recursing and now we are out of threads and no task has been finished?
If you're out of threads and no task has been finished,
Yeah, because we keep on recursing like that.
eventually you would have to reach the end of the recursion. And then so you have to
We have
stop
open a
making
task
tasks.
and then in the next recursion, we'll open a new task.
Yes.
And we'll have a list of the tasks, but like now we haven't reached the end for any task.
Yes, you don't have to, there's no guarantee on like when the tasks are completed. You have some, you just keep making the tasks and then eventually you stop making the tasks. And maybe some of the threads started completing the tasks while you were making tasks, but maybe not.
Can you be out of threads? Like,
You can have more tasks than threads. But like you're never gonna, here you won't have infinite tasks, like eventually you reach the end of the recursion. And so once you reach the end of the recursion, then you have some tasks that the threads need to complete, and then those tasks are assigned in some order.
You have, you have 30, suppose you have 30 cores or 30 threads,
Mhm.
but you are calling, at a point where you have all the cores used, but it is still calling for a
yeah,
lower recursion, I mean, lower fib file.
Mhm.
And because you don't even have a single thread to do serialized operation, how will OpenMP resolve this?
What do you mean you don't have a single thread to do the serialized operation? Like each of the threads is spawning fibs.
Yes.
Yes.
Suppose, suppose n is 60. Okay, so, it should spawn, say about, not sure, but at least.
Like 2 to the
60, right?
60 tasks, because each one spawns 2.
Yeah, but then you have only,
You have,
two questions out here. First one is you have only 30 threads,
Mhm.
which means at some point there is a deadlock.
no,
Because you
Why
don't
would
have
there
enough
be a
threads to call more threads, right?
I think thread is assigned when you like reach the end of the recursion and then you actually start executing the like computation. So basically you don't like thread is not doing anything before you like call the end of the recursion. So that's why like to the point that you didn't come to like n equals to 2, then you have thread like available. That's why you wouldn't have a situation where thread is not available.
That's not the case, right?
I'm not sure.
I have
sorry,
n
I don't think I understood the question. Can you say it again?
will put n, call
Yeah.
n minus 1, n minus 1.
Yeah.
And then think of n minus 1 calls n minus 2.
Yes.
So then it cannot reuse the thread, right? So while it is being operated. So the end, at the end, when n is less than 2, it returns and only then can it free up all the threads, right?
Sorry, is this a comment about this?
So he's confused between software threads and hardware threads. He thinks he can only spawn 30 threads because there are only 30 cores.
Oh, no. There can be arbitrarily many software threads. The software threads are logical things built on top of the hardware.
It cannot compute the values into.
Like some processor needs to continue managing the task queue.
Yeah, there is a manager process.
Yeah.
Right? And then there are child threads, right?
Yes, and then the manager needs to, there somehow always needs to be a mapping between the tasks that you computed and the underlying hardware threads. And somebody, like that process cannot stop regardless of how many like work tasks in the program you made. That's like something independent of the program. So, okay, so you're saying like, so you have tasks. Okay, you can think of like these tasks are eventually mapped to some thread, but it is not necessarily the case that like once you spawn this task, it will immediately get assigned to a thread. It just gets put into the queue to eventually get assigned to a thread. So like there's no such thing as like running out of threads because like the manager will always make sure that you have a thread that can continue to assign the link. Is that answer your question?
Okay, I still have a question, but are these two X and Y called simultaneously or is X being evaluated then Y is called?
No, they're logically in parallel. So they can happen in any order. And they can also happen at any time. Like, I mean, this one needs to happen before its children, like eventually you're gonna come back up.
Yeah, because we have that.
Yeah. But like these two can happen in any order.
One more question. So if you have fib n and fib n calls fib n minus one in the x, and fib n minus one ultimately goes down, right?
Mhm.
And until it reaches two, will all these threads be freed from the hardware thread?
Not necessarily. The scheduler can assign any, like, as you keep going down the recursion, like the scheduler could assign, well. It has to respect the recursion dependency, so like you cannot compute, like this thing will eventually call to n minus two and n minus three. And those things underneath, like n minus two and minus three, need to finish before you get to this one.
Yeah, but then it may not, while it is being finished, it may not be occupied. Fib n minus one need not occupy a thread, like a hardware thread.
It might not.
Okay.
Good question.
The
Yes.
dependency is maintained by OpenMP. That
The recursion dependency is
Yeah.
just like by the program, and then the thread scheduling is not in
Yeah,
the
not the
program.
thread scheduling, but the dependency is maintained by OpenMP.
Yeah, because of the task weight.
Yeah.
Yes. Uh-huh. Okay. Okay, so that was parallel tasks. There are also other constructs in OpenMP, so you can also define parallel for just with pragma or OpenMP parallel for on top of your regular for. And then you go from this example, like I up to n, and here you're just adding two arrays together and multiplying. Yeah, you're adding two arrays together and you're showing them y and multiplying x by some constant.
Does it always work, like regardless of what kind of for and what's inside the for body is? Because like I can imagine some case where like inside the for have some cross dependencies, whatever, where like threading can be a bit messed up. So I'm wondering whether this private just handles everything.
What do you mean handles everything? Like,
I mean, if I
If
have
it's
a for thread, it doesn't matter what's inside the body. If I have a for loop, it doesn't matter what's inside the body. OpenMP would handle this.
if you're like, OpenMP, like, so here, this is a very nice example because everything is independent. If they were dependent, OpenMP does not handle, like, you would need to manage need to manage, like, if stuff depended on each other, you would need to manage that yourself.
Okay, so OpenMP wouldn't change anything. We
No.
would have this pragma, but.
Yeah.
these different-
This pragma just says like everything in here can operate independently, but if truly like some of the stuff inside depends on each other, then you have to use some other constructs to manage the dependency, and I'll show you how to do that later.
Would OpenMP only work with multiple threads or can you vector processes for the?
OpenMP does not help or hurt, or like this pragma does not like improve the compiler vectorization or anything like that. The compiler vectorization, like whether it uses the vector unit, is like something independent.
OpenMP itself wouldn't use the.
Yeah, OpenMP does not guarantee that you're using the vector units. It's just for the threads. Okay. And yeah, in addition to the parallel for, so like you may have many more tasks or loop iterations than you have threads. So you have to divide up the tasks or the iterations among the threads, and you can specify that with the schedule clause. So you can say schedule, and then you have a method, and you have a chunk size, which is how many iterations you assign in each like chunk of your work. So the methods that you can specify, you can say static, which is the default schedule, which divides the iterations into evenly sized chunks according to their size, and then distributes the chunks in a round robin way. So this is an example of static. So suppose you have 4 threads and 100 iterations. And if you just say static, it divides it evenly. So like 100 divided by 4 is 25, and each of these got 25. If you specify 20 as your chunk size, then your work pieces are size 20 iterations. So you have like 20, 40, 60, 80, and then you come back around here to 100, and because it's scheduled in a round robin way. And the other one you can say is dynamic, which means that every thread gets some iterations, and then once you've finished the iterations that you grabbed, then you can take the next work chunk. So for just straight dynamic, the minimum size is 1. So you grab 1, 2, 3, 4, and then you have no guarantee on what is going to happen after that. But once you finish this one, you take whatever is available next that you see in the queue, and then you keep working on it. And if you're dynamic with the chunk size, you can make the minimum size bigger of the section that you can grab. So here would be 10, 20, 30, 40, and so on. Okay, so there's some question earlier about what like why you would specify something as shared versus private. So this is an example. It's a very simple program. We have some int x and we set x equal to 44. And this is the parallel 4 up to 10. And we set inside the parallel 4, we set x equal to I. So we set it to the iteration variable. And then we print what number we are. And then we print x. And then at the very end, after the parallel 4, then we print x is something. Okay, so here we had a parallel 4 and we specified x to be private. And private means that everybody inside gets some uninitialized local copy of the variable. So like this is the output that you would get from this program. And because like x was uninitialized, but we just set it here. So that's why we're printing like these loop iteration variables there in any order. There's no specified, it's just an example of how the threads might have been scheduled. And at the very end, then we print x is 44 because none of the values persisted outside of the parallel 4 because it was declared private. Does that answer your question?
Now, why don't we use another name? Why don't we use like T?
Instead of using x? You could, I guess so. Yeah, then it would be just like. Huh?
No, but I'm also wondering, like, whenever we use private, that means that we just forget whatever we defined before, right?
Yeah.
So basically, we just say, okay, we can use this memory for that.
Mhm.
But it's not, for each thread, it's gonna be different ones, right? So it's
Yeah.
like not the same, I mean. So then, what would be the purpose of coupling, like, something that we used before with this private thing, we just could have said, like, we haven't used it.
I don't know, I guess if you don't, yeah, I guess maybe if you wanted to declare them all up front. Yeah, I'm actually not sure why, because you could just, if you were using it in this local way, you could declare it just inside the 4. And especially because it's uninitialized, like it doesn't really matter whether you did it before or not, so. Yeah.
X was shared, the last print would print something between 0 and 10.
Yes. Yeah. But you want, it would be any of them.
Yeah.
Mhm.
Why are the thread numbers, for example, are the 0 are?
Because here, just because, it doesn't have to be grouped, like there are fewer threads than iterations, because we had 4 hardware threads. So that's why, like, we printed this OMP thread number. They happen to be scheduled this way, but they didn't have to be.
Just to, so I have my understanding, if X were shared, this printing on the end would also be screwed up, right? Because like, some thread could also, would some thread also be able to like overwrite before it like prints?
Yeah, like you might not get 10 unique numbers here, but you would get 1 unique number there.
What happens if you not explicitly state private or shared?
Default is shared,
Default share.
yeah, unless it's an iteration variable.
Not the schedule clause, like where do you specify that in the code? For example, like you see the imported, right, so how do you specify that exactly?
You would specify it like after 4. I think it can be like private or schedule can be in any order.
Maybe you're calling like incorrectly, but I remember like print isn't like exactly like it prints right away. There's like some like queue and then it flushes it. Is that like something that like you want to think about when you're doing like shared memory program like this? And is that also maybe a reason why like the thread numbers are grouped together with that?
But here they're flushed because there's a n.
Oh, okay.
I think they're probably grouped just like due to the scheduling is probably not scheduling 1 iteration per thread.
Each thread will have a print buffer, separate print buffer, or they write to the same standard output.
They all write to standard out, so like, it could be that sometimes when you write, sometimes when you do printing with threads, like you can get stuff in the middle. Like like this is a very nice output, but like you might have like thread and you have like thread number inside it. So there's not even any guarantee on, like, that you get the full string before some other thread happens.
What about happening if I declare this the parallel 4 is shared memory?
Like if you said private X into the, then the X would be in the range, like the print X at the end would be in the range of 0 through 10, but you may get duplicates because X is continually getting overwritten, so like you may print something else before you overwrite it.
Got it.
So that is private. And then there are some special cases of private in OpenMP. So there's last private, and the way that last private works is that it keeps the last value of X in the last iteration. So again, this is like up here was the same as before, and now X is 10. Previously X was 44. And then there's also first private, which initializes everybody to get the value that it had in the beginning, like before you declared it outside. So in the beginning, X is 44 for everyone, but then you just overwrite it with I. So that's why here, this is like the same output that we got in the first example. But it just have like if you were to print X here, you would get 44 for everybody. Yeah, so OpenMP also also includes reductions, which is like a nice syntactical way to express parallel sum or parallel any other operation that you want over some iteration variable. So this is how you use it. N is something big, you declare the two arrays, A of n and B of n, and then you do some initialization here of some random values. And then we specify parallel for parallel 4, then shared, private, I is private, the schedule is static, and then you specify reduction. So the inputs to reduction are the operator that you want and the output that it's going to go into. So we declared result up there. And here, this 4 is parallel, and result is result plus some multiplier of the two things. And if you didn't have a reduction and you just made result shared, then you would get some garbage value because everybody's writing to this concurrently, and so you have no guarantee on what the value is. But because OpenMP does manage this for you, so you can just write result, and then you would get the correct sum. And you can also do other things like not just sum, you can do multiply, you can do bitwise operators like or and and you can do logical operators like or and end. That make sense?
You said that iterators are always private, so you don't need to actually declare as private.
Yeah, you don't need to declare it. That's just extra.
How does the schedule static work in this case?
Static means that everything is cut up front. So it would cut this for loop into whatever default chunk size was defined, and then it would sign them round robin across the threads. The management of result to make this correct is independent of the schedule. Was that your question?
Can you please repeat one more time what exactly this reduction does and what would be the difference comparing to what we have just had pragma on the parallel 4 and then private for result? Like, why would it be?
Then if you put private for result, every iteration would have a different copy of result. And so you wouldn't get the result. In the end, you would just get, well, if it was private, it would be nothing because result was not initialized up front. The reason that the reduction is so that everybody can safely write to this variable result.
Again, how exactly do we have garbage value when we have said that it's shared? Like what's the case there?
So you're saying you want the result to be shared?
Yeah.
Maybe like, in a minute, I'll explain more about why you can't do multiple writes at the same time, but the reason basically is that if you have two threads, like let's say thread one wants to write one, and then thread two wants to write two into the same location, you are not guaranteed that either, well, you're guaranteed that at least one will show up in the end, but you're not guaranteed that any specific one will show up in the end.
Mm.
Maybe I'll keep going a little bit and then see if that answers your question, and then we can come back. Okay, so yeah, the main issue when doing parallel programs is kind of like you're saying, there's something called determinacy races, and the way that you solve those is through mutual exclusion. So a determinacy race is what happens when you have two logically parallel instructions that are going to the same memory location, and at least one of them is doing a write. So this is like a very simplified version of the sum. You have int x equals 0, you have parallel 4, you just have two iterations, and you're doing x plus plus. And so you started with x equals 0, and then you branched off x plus plus into these two, and then in serial, this would be x equals 2 at the end. And so you're going to assert this. But because of the way that parallelism works, so you started with x equals 0, and the way you do this is like through registers. So you load x into register 1 and register 2, you increment the registers, and then you write them back into x. And yeah, so here you're not guaranteed that this is going to be 2 in the end, because like this, each of these has a view of x that started as 0, or it could have started as 1, you don't know, because the instruction can happen in any order.
How exactly then this reduction that you showed before works? So like how does it make sure that this thing is actually like implemented the way it should?
It's a good question. So I think it depends on the implementation of OpenMP, like how you would implement reduction. We will talk about how to do parallel sum later. For some, there are algorithms to do parallel sum. For other more, I guess you can implement parallel sum for any operator. So we'll talk about that in a future lecture.
But she's gonna show like a general way of how these things.
Yeah.
With meters.
Yeah, with mutexes, but like specifically for reduction, there are like fancier algorithms that you can do. Okay, so there are several kinds of races. Like I said, races happen when you have two instructions and at least one of them is writing to the location, to the same location. And so you have these two instructions and both of them are logically in parallel. And you have, if you have two reads to the same location at the same time, there's no issue. Like they're just gonna read the same value and you would be fine. If at least one of them is writing, or if exactly one of them is writing, then you have a read race because you're not guaranteed which copy you will read. And if two of them are writing, then you have a write race because you're not guaranteed which copy you end up with. And we call two sections of code independent if they have no races between them. So the way that you avoid races when you program is ideally you should make your iterations totally independent if you can. And if you're doing task spawning, between the task spawn and the task wait, ideally the code of the task that you're spawning should be independent of the code of the parent. So that happened in Fib just because Fib is a very simple example and you're just doing computation, like there's no memory writing. But ideally you would do it for everything and you may have to do it carefully. But if you cannot, then there's something called locks. So locks are this form of mutual exclusion, and you implement them or you use them if you have to access the same data in parallel. Then you have to use locks to protect it. And this is just one way. It's just basically like a value, and it can only be held by one thread at a time. And the high level way that these look is that like you have a lock and you have this parallel for, and lock implements these functions set and unset, and only one lock or one thread can set at a time. So if like it doesn't, you're not guaranteed which thread will set the lock, but only you know that only one thread will set it, and so and then everybody else will have to wait to get it. So you cannot proceed past this line until you have set it. Only one thread will set it, and the thread that sets it can continue into the section. And once it's done, you unset it, and everybody else can try to get it. Does that make sense? Okay, good. Oh, yeah, and they're not cheap performance-wise, and the way to think about that is that everybody has to have a view of the lock. Every thread, every private cache, like what we were talking about earlier with MSI. So once you unset or set the lock, then it becomes invalid in everyone else's cache and you have to reload it. So the exact way that you would implement them in OpenMP is with just the syntax. There's a little bit more complicated, like you have to initialize it. Like I said, you have set and unset, and then at the end you have to destroy it. And like this is the exact syntax that you would use in OpenMP, but it's pretty much the same idea as the high level thing that I just showed, which is you declare the lock, you initialize it, you have this parallel loop where you set it according to like some thread will set it. And this is the region that is protected by the lock. And then once you exit the for loop, you're done with the parallel part and you can destroy it.
Yeah, what kind of, like, I assume that init and destroy are for some kind of security.
Probably just for, to make sure that you it's probably just to make sure that it initializes the values. Like, so basically, you can think of a lock as like a bit, and it's set or unset, and probably init is just to make sure that it's unset in the beginning. Because like when you declare this thing up here, like this is just, like lock T is just like garbage values. Like in C, when you declare the value, like you're not guaranteed what's in there until you set it. So that's probably what init is for, and then destroy, probably for memory management.
Let me guess, why do we need an open MP lock instead of just the normal lock that we had before? Like, what difference is there?
Oh, it's the same. This is just like the syntax that you would use in OpenMP. Like you can implement, I think like C++ might implement it. No, it's just in Open, it's just like they implemented it for you. Like you could implement your own lock and you could just, like you could do it in C++ and you could use it in your OpenMP code. And that would be totally fine. This is just like, it avoids you having to do that.
I think I had a similar question. So like, I think prior to that class, we all had to do some multi-threading programming or whatever, and it would be like always the same, like set lock or set lock, but we've never used OpenMP. And the question is basically, what's the benefit now? Because like what I would have thought before introducing OpenMP that it's going to be managed automatically for me, but probably not. So I gotta set it anyway, right? So like, does it provide like a better interface or like better management of the thread? Or what's the actual purpose of using OpenMP compared to like this traditional? I don't know exactly what's the name for like the just
like pthreads, you mean?
locks.
Oh, like STD thread or something?
Yeah, probably.
Yeah, you could use like STD thread, it's probably
No,
similar.
Other than
Just like different syntax.
Okay.
Yeah, and just that this one is popular. You could use any, I mean, the homework is in OpenMP, but like from a general standpoint, like if you're trying to choose a threading library, you can use anything. OpenMP is a good one because everyone has it already, so you won't run into much trouble with compilation like for other people. But in terms of like choosing one, I think once you understand like the high level constructs of like parallel for and parallel task, every language would be able to support those in some way. With pthreads, like you have to manually implement your own parallel for. Like I was showing the create, and basically you would wrap create into a parallel for syntax, but like you could implement it yourself if you wanted. So yeah.
What's the difference between using the shared like keyword with the pragma thing and then using locks?
If you have shared, then everybody can write to the same variable. But if you have locks, then like suppose you didn't have the locks, and then you had declared some variable above a shared, and like just x, like in the example that I had before, and then you were doing x plus plus in here. You would not be guaranteed that x would equal to n at the end of this loop if you didn't have the locks. Because in here, like when you load x, you're not guaranteed to load, like when you do it in serial and you're doing x plus plus, you're guaranteed to load the result that you got from the previous iteration. But here, you're not guaranteed to load any previous iteration. Like it could just be the one that you got at the very beginning.
So if you're writing something, then why would you ever want to use the shared? Like, wouldn't it always be best to use logs if you're writing?
If you're writing to share it, if you don't, if. It's a little more subtle, like if you know that it's safe to write to the same thing and share it, then you can just keep it as shared. Like if you, for example, like sometimes you might not care what the value is, or like you can accommodate a range of possible values. Or like if you know something about your program and you know that everybody will write the same value eventually to it, and you don't care what order they get written in. But it depends on your program.
So OpenMP then doesn't distinguish like exclusive or shared logs, it just says one log and it's always exclusive then for the thing.
So is it the same to like the reduce thing that you just introduced?
Like the lock?
You said that
Yeah, so you would not want to implement reduce with just one lock because this would serialize your entire for. Like if inside your code was like x plus equals like a of I, for example, like only one thread can enter this part at one time. So it would basically be the same as single threading. Maybe even worse because now you have lock overhead.
But if you do reduce, then
If you do reduce, it's not serialized. Under the hood, OpenMP manages some fancier thing.
Yeah, so OpenMP also has its atomic read write. Right?
Yeah.
So, I'm not sure what else would this have that atomic read write does not.
Just ease of programming. Like if you're saying like you want to implement the locks with atomics.
No, I'm just assuming that logs would have something that is a superset of atomic read write.
Locks are implemented with atomic read write.
Okay, so they are both equivalent.
Well, they're not, I mean, the lock could be implemented in a lot of different ways, like, it could be like a spinning thing, like a spin lock, or like a sleep article, a lot of different locks. I don't know what this specific thing is doing, but it's not, it wouldn't just be like checking, like while, test and set equals 1 or something. I'm sure that's probably not what they're, or maybe that's what this is, but there are other things you could do to like create a lock.
Oh, I'm not asking about how to create a lock. I'm just asking what are the use cases that the atomic read write might not cover.
Oh, I think atomic read write is like just one level below this. Like this is just ease of programmability, I think. In terms of functionality, you can implement this with atomic read write. Okay, good. So now I'm done with talking about OpenMP syntax, and I want to talk a little bit about how you measure parallel programs. So the main thing that we're interested in when doing parallel programming is scalability. And scalability is the ability of your hardware or your software to deliver greater power when you get more resources. And in parallel computing, we define speed up as T1 over TP, where T1 was the serial time that you ran on one core or one processor, and TP is the time to run on P processors. And these are examples of speed up, like this is the number of processors that you got, and this is your speed up factor, how much time faster you got. Perfect would be linear. In practice, you don't usually get linear, but you get ideally close to it, and you can get like shades of worse. And this is poor, like if you have, this is pretty much no scaling. So I talked about Amdahl's law in the first lecture, and Amdahl's law, there's two kinds of scaling that we're interested in. The first one is called strong scaling, and strong scaling is the speed up that you get given a fixed problem size. So strong scaling is like you fix the problem size at some input, and then you give it more resources, like more cores or more threads. And the speed up by Amdahl's law is bounded by the serial fraction. So here, S is the fraction of the work done sequentially, and S is the work done by the best sequential algorithm. 1 minus S. So 1 is like the total work, S is the serial fraction, 1 minus S is the parallel fraction, and P is the number of processors. And at best, you can speed up this 1 minus S part. And if S is less, then your total parallel speed up can be higher. And the speed up that you could possibly get on P processors is bounded above by 1 over S, where S is the fraction of your program that was serial. So for a fixed problem size, the upper limit of speed up is determined by the serial fraction from Amdahl's law. And for weak, so the second kind of scaling is called weak scaling. And in weak scaling, I guess like the main thing to note is that for strong scaling, you fix the problem size, and for weak scaling, we notice that usually the problem sizes are not fixed, but often they scale with the amount of resources that you have. Like you're trying to solve bigger problems if you have more cores or more threads, like you might not want to solve tiny problems. So Goofstitz's law is like a similar analogy to Amdahl's law in that it is based on the observation that you can only scale the parallel part. And it basically makes this assumption that the serial part does not increase in terms of the overall size of the problem when you increase the size of the problem. And so you get scaled speed up, which is which is equal to your serial fraction plus your parallel fraction times p. And because this is like the part that you can speed up with parallelization. And weak scaling, when you measure weak scaling, you calculate it on different problem sizes. Usually you scale the problem size equal to the amount that you scale the resources. Okay. So a short example, suppose we're trying to compute this Julia set, and a Julia set is some mathematical thing, and it's associated with this complex function. And basically for our purposes, the only important part is that it can be made into an image by converting some function into pixels on the complex plane. And you don't even need, it doesn't matter how you compute this, but the important part is that you can parameterize it by h and w, which are height and width. And basically you have like an image parameterized by width and height, and you need to do some computation per pixel. That's all you need to know for this. And so like the way that you would do this and that the pixels are independent. So the way to do it in OpenMP is you just put a parallel 4 outside the top, and you do some iteration over height and width, and you do some calculation in here. So the way to do the strong scaling, like I said, you vary the number of threads and you keep the problem size constant. So in this example, we had height and width as the 2 parameters. And here, height and width are both fixed at 1000 and 2000, and only the number of threads is changing. And we are measuring the time that it took with the variable number of threads. And this is the plot that you can generate from that data. You generate each one of these by dividing P1 over P, where P is one of these, and P is like the value on the x-axis that corresponds to it. And the other kind is weak scaling, and you get weak scaling by varying both the number of threads and the problem size, and you vary them both proportionally you vary the problem size proportionally to the thread count. So here we are doubling the number of threads, 1, 2, 4, 8. And here we are varying the height proportional to how we vary the thread. So like here the height is 1000, you have 1 thread, here the height is 2000, 2 threads, and the width stays constant. So the total size of the problem, which is defined by height times width, is varying equal to how you vary the threads. Then we measure the time, like experimentally just measure it. And this part, like, it's a little hard. Okay, so intuitively, ideally, if you vary the resources and the problem equally, ideally you would keep the same runtime. So like all of these times look pretty much similar, but of course, like we don't live in an ideal world, so we're going to get a little bit worse as you get bigger problems and more thread count. And the way that you plot this thing is, the way that I find it easiest to plot it is you calculate efficiency, where efficiency is P1 over TP. And lower efficiency means that more threads and bigger problems took longer. And so like efficiency goes down, and then you multiply that thing by P, where P is the number of threads that you got. And so like ideally, so that gives you like ideally still linear speed up. Because the highest efficiency that you can get is 1. Modular, like you can, in terms of experiments, like you can see this is a little bit better than this, but like they're basically the same. Like this is 3.9, this is 3.8. Similar. So to wrap up, processors today have multiple cores, and to get high performance on them, we have to do parallel programming. However, doing it directly on the processor cores is painful and error prone. And OpenMP abstracts the processor cores, and it handles the underlying synchronization and communication, and it implements load balancing. And you can choose what schedule you want for the load balancing. And for any parallel program in OpenMP or otherwise, scalability is important for measuring how efficient your parallel computing is and how well you use the resources. And homework 2 is in OpenMP, and you're gonna, in homework 2, I asked to generate both strong scaling and weak scaling plots to test like just how you do this. But you can use the examples that I showed to like give an idea of how you would, how the data should look like and how the plots should look like. Okay, thank you.